Hey guys, can you hear me? Sup, sup, sup. I see you. Way to be there, September. Hey Amanda. Hey guys. Hey guys. Hey guys. Way to be here. Look, I got an early bird for you. How's it going? This rainy afternoon. We're cooped up in the house. Are you ready to go again? We just have one thing to cover tonight. Isn't that nice, September? Just covering composite functions. Hi, Rachel. How's it going? Whew. Another week. We made it. This is week 2. Wow. That's pretty impressive. Entire mile? That sounds hard. You ventured outside? Wow. That's pretty impressive. I'm impressed. I'm impressed. I'm impressed. It's nice. I want to be able to do that. Maybe by next week I'll be good enough at this virtual teaching thing that I don't have to spend 24/7 at it. Maybe next week I can just teach, maybe have an hour a day, and then I can go run from here to the corner. That would be good. That'd be good. That'd be good. Whew. Another week though, week 2. I think we just have 4 more weeks. 4 more weeks. Hey, that's really good. A 12-minute mile? That's really impressive. That is impressive. I like it. Out and about, staying healthy, just stay away from everybody else. Ugh. So I have y'all an early bird. Y'all remember doing this on the before spring break? I mean, I think a 12-minute mile is impressive because it takes me 20 minutes to go a mile. So 12 minutes, I mean, let's see, it's like 3/5 of the time, 60%. HEB is terrifying, is it really? There you go. There you go. It's a shower wall. That works. Hey, that is a teacher being inventive. I'm kind of impressed by that inventiveness. But you're right. I already had my setup. I knew long before, 3 years ago, that this was going to happen. I was ready to go. I was prepared for the pandemic long before it happened. This is just what we do in my house, though. So, we just school all the time. But I'm impressed with it. See, I told y'all, use your shower walls to write on. I told y'all that was a good place to write. Put your notes up there and study off of there. Or did I tell y'all that? Maybe I didn't tell y'all that. Maybe it's just all my other classes. I tell them to get their crayons out and write on their shower walls. They make those cool markers and crayons for the showers. It's a great place to study. Or on the windows of your mirror as you're getting ready in the mornings. You can use those crayons in there too. So before spring break, we did this function notation. You remember doing that? If you're here, say hi so I know you're here. Let me know. Miss Simpson over there says that y'all are lurking. Just let me know so I can give you bonus points for being here. So here we've got our function notation, and we're going to put this, remember we just substitute that in everywhere we see an X? Remember doing that right before spring break? Hey Fernando, way to be here. So I'm going to do that. I'm just going to take this value and replace it in everywhere I see an X. That's all that function notation says. Normally we're looking at something like this. It's just like f of 3, and we put that 3 in there. We put it in there into the x and solve. But when we did the function notation lecture, I also had us put in just some expressions. And that was to build up for exactly today. Maybe I can help you through it, September. We'll get you through this. So, for instance, in this one, I'm just going to put this in for x and simplify. So here, instead of writing here, I'll write it again. F of x plus 4. Instead of writing that x, I'm going to leave a blank. And I'm going to fill in with this x plus 4. Just instead of writing that x, I'm going to write this x plus 4. Hey, Marissa, way to join. Yay! All right, now I'm just going to simplify it out. So all I did was replace my x with that x plus 4. That's what that function notation tells me to do. So now I'm just going to simplify it. Remember that squared says to do this twice, times itself. And now we multiply it out. So, I don't know, do you want to do the 2 times that first, or do you want to do this times that first? Whichever one. Yeah, I like to do the 2 first. Hey, Thomas. Welcome. I'm glad you're here. Way to make it. Now I'm just going to multiply, distribute this. So 2x times x equals 2x squared. 2x times 4 is 8x. Now I'm going to do this. 8 times x gives me 8x. And 8 times 4 is 32. Subtract out that 1. You get 2x squared plus 16x plus 31. So, if you were able to do this early bird, then you were able to do today's lesson. There you go. We've done it. There's our lecture for today. Because this is basically what we're doing. We're just going to do it in some fancy writing. Some fancy notation is all we're going to do. So, now what? So let me explain kind of what we're doing. Okay, so we have 2 functions here. But this is all we're doing. We're just going to be replacing and then simplifying. Bada bing, bada boom, and we're done. So here we go. Let's start by just looking. We actually have 2 functions. We have a linear function here that I'm going to call g of x. That's what we have. We have this linear function. Hey, when do I get to go home? What do you mean? What do you mean? And who is that? So I can give you bonus points for being here in class tonight. So here we go. I'm going to take that x plus 4, and that's just some linear function. So, I've got some functioning machine. Remember my Coke machine where I push the button and every time a Dr. Pepper comes out? So here, oh, hey, Joe. Here I'm going to put this x plus 4 in there. And let's just pick some number to put in the machine, some input into the machine. So pick something like, 3. If I put 3 in this machine, 3 plus 4 gives me 7. So every time I put in 3 in there, I'm going to spit out 7 every single time. Yeah, September's right. We get to go home. Well, I think we're all at home, aren't we? Shouldn't we all already be home? Okay, now I'm going to take that function. I'm going to put this output. I'm going to put this 7 into a new function. And this new function is my f function. So I'm going to take my output from my f and put it in Thanks, Amanda. Good job. I don't know a Joe, so I'm glad you're on here tonight. Okay, so now I'm going to take this and plop it in and see what I spit out there. So I've got 2 times the 7 squared minus 1. That gives me 49 times 2 minus 1. Well, that's 98. So I got out 97. Okay, so what in the world did I just do? What in the world did I just do? It's just some machine. You remember our Coke machine analogy, September, where I put some money into my Coke machine and out comes something? So that's all I got here, is I've got my function. I'm putting in an input, something's happening to it, and out comes an output. And I started with a linear function I put in, and I got this output. Now, I'm going to take that output and put it into my next machine, put it in, and out comes that output. Okay, so I had 2 functions to begin with. What we did over here is we created a whole new machine that does the work of both of those functions. So we created one machine that does the work of both of these. So I'm going to be able to put 3 in here, and I should get out a 97. It should pop out a 97. Let's see if that happens. So what we did is we put in 3, and let's just see if it really does work. If I put in 3 right here, so that I have 3 squared is equal to 9. And 9 times 2 plus 16 times 3. Can y'all see that? It's kind of small down here. Yeah, it is just a visual. Yeah, you're not going to have to do any sort of designing. Nothing like that. Okay, so I got 2 times 9 plus 16 times 3 gives me 48 plus that 31. Can you see that? It's kind of small. Okay, good, good. Okay, so 2 times 9 gives me 18, plus 48, plus that 31. Let's add all that together. And that gives me 64 plus 31. No, that doesn't look right. 66 plus 31. Which is 97. Look at that. That was the same thing that we got out over here. Kind of crazy, right? So here's what we did. We put in 3 into this machine, and it did the work of both of these. So that's all a composite function is. So what we're going to do today is exactly this. We're going to have 2 functions that we could put an input in, figure out what it is, spit it out. Put an input in and put it out. Or we could take both of them and make one function that does the work of both of those. So I always thinking about this is my machine with ice. I'm going to go get some ice for my cup. And then I'm going to get Dr. Pepper from this other machine. So this machine gives me ice, this one gives me Dr. Pepper. So I put in my money, get out my cup of ice, get my cup of ice, and then I get a thing of Dr. Pepper with ice in it. But, at Wingstop nowadays, they have this fancy machine that does both of them at once. Now you just push it and it gives you ice and Dr. Pepper. Oh my gosh, it's clever. And that's what this composite function is going to be. So this is college algebra. We're learning some college algebra and some composite functions today. Come on in. Yeah, that's what happens. This is the first time I've had that. We're just strangers are coming in, but come join us. We're learning college algebra. Feel free. Okay, so what we did was notice this right here. I could replace that with this g of x. That's what we did, g of x. So, right in here, I could replace that with g of x. We read this as f of g of x. That's what that says, f of g of x. We can also do it the other direction, like this, where we do g of f of x. I know, me too. I too go random into random math streams. I mean, that sounds like fun, right? See what math you can learn. I'm all about it. The public can come join us, see what all they can learn. It would be great. Teach all of America. Okay, so notice that this one looks different than what we did over there. I want to see if I get out that same machine. Does it turn out to be the same thing? Let's just see if it does. So the way this works is this time I'm putting it in my f of x machine first. Or I'm going to rewrite this. Instead of writing it f of x, I'm going to write it with this 2x squared minus 1. So see how I just erased the f of x? Or maybe I should leave that there so I don't lose anybody. I'm just going to, instead of writing that, I'm going to write it as 2x squared minus 1. Now what I'm going to do is take this and put it in this g function. I'm going to put it in this linear function. So everywhere I see an x here, I'm going to replace it with that 2x squared minus 1, like this. 2x squared minus 1. And in this case, 2x squared, well, I can combine those guys to get plus 3. Notice that when I did it the other direction, this function and my f of g of x function are not the same. They don't look the same. So what this one does is it takes my f of x function. So here's my f of x, which is this guy. So let's say I put something like 3 into that one. Well, 3 squared is 9. 9 times 2 is 18. Minus 1 gives me 17. So my output there was 17. I'm now going to put that into my g of x function. So this output goes in, and I'm going to put it into this g of x function. 17 plus 4, well, 17, 18, 19, 20, 21, and I get out 21. Notice that it's not the same this way. So in other words, if I get my cup of Dr. Pepper first, and then take that cup of Dr. Pepper and put ice on top of it, it's completely different than if I put the ice in first and then Dr. Pepper. Those are two different things. I like my ice in first and then my Dr. Pepper. Don't do it the other way. It tastes different. And that's how this function notation works as well. That g of f of x is going to be different each time than my f of g of x. So those are actually going to end up being two different functions. But notice all we're doing, we did this back before spring break. All we're doing is taking one function and putting it in for the x value in the other function. And that creates one function that does the work of two. Now let's just check ourselves. If I take this, I sent it through both machines. But I want to check to make sure I've got a working machine. This should do the work of both of them. Like this. So if I do g of f of 3, if I put 3 in there, 2 times 3 squared plus 3, Well, 3 squared is 9. 9 times 2 is 18. 19, 20, 21. Sure enough, this new function does the work of both of them. That's kind of cool, right? So we're creating one function that does the work of both of the other functions. Kind of nice. All right, let's do some more examples. That's a good warm-up. There's your early bird that led into the lecture. You've already done it. You've already done this. You did it before spring break. Yay! So maybe it won't be too bad. Hopefully, maybe. So let's do another example. Here's another example. What kind of function is that? What kind of function do I have there? What kind of function is that right there? You remember? That one's a square root function. We learned that parent. There's our little spout and our teapot. And then here I've got L of x. I think they did. It's kind of obvious too because nobody answered that question. That's okay. I'll just keep pretending that they're here. And then later when they come back to watch it, they can watch it then. But yeah, nobody's actually here. Okay, so then x plus 4 is my linear function. So this one is a square root function, and there's a linear function. And here's what I'm going to do. I'm going to find S of L of x. So I'm going to find a new composite function that puts both of those together. Then why didn't you answer my question? I asked what kind of function that was. Nobody answered me. I was just staring at a blank room. Y'all are all looking at me like this. All right, so I'm going to take this linear function and put it in my square root function. I like to rewrite it so that my x plus 4 replaces that L of x. And now I'm just going to take that x plus 4 and replace it with that x. I can't really do any more simplification. There we are. That just went inside there. So notice when I put this linear function in that square root function, I get a new square root function. Now, we know how to graph that. What's going to happen? What's it going to look like? Where is it going to go? If I wanted to graph that function, what would that function look like? What would that function look like? What would this function right here? If I wanted to graph him, what does he look like? Hey, Robin! Woot woot! Oh, that's a really good idea, Robin. I will definitely do that at the end. I think that's a great idea. So, oh yay! Y'all are here. We're going to go to the left 4 units. So I'm going to take it and pull it to the left 4 spots. So 1, 2, 3, 4 spots to the left. And I'm just going to use my parent. So I know the parent of the square root. The parent looks like that. Y'all just know those points like that, right? And that's right. It is the spout on my teapot. So I'm going to take it and subtract 4 from all my x values, and that's what's going to move it to the left. Yay! Rachel didn't walk away, turns out, after all. So I've got my points at -4, 0, -4, 0, -3, 1, 0, 2, and -13. Oh no, something's wrong with that. No, that makes sense. What did I do wrong? -3, 1, -4, 0, 0, 2, and this is a positive 9. That's what I did wrong. So a -4 plus 9 makes 5. I'm adding that -4. 1, 2, 3, 4, 5. So at 5, 3. So on the first, yeah, thanks. On the first 5 of your homework on this composite function, you're going to create the composite function, and then you're going to get to practice again those transformations. So I want you to do exactly that. I want you to use your parent and show me what they're doing. So you need to start with the parent somewhere on there. Definitely. I know, Robin, it is killing me too. So this is exactly it. You stay with me on the live stream and you can ask questions as we go along. That whole watching video things is hard. This is like being in class. Now we're back in class again. All right, so we created this new composite function and then we graphed it. Now we can check to make sure that our composite function really is correct or that we've done it correctly. And the way we can do that is we can start inside of here by picking some value, like 2, and just plugging it in. Maybe not 2. How about we do, what would be a good one? How about 8? No, how about 12? Let's try 12. I'm going to input 12 just to see what happens. So I'm going to take that 12 and put it into L. And I get out 16. Now I'm going to take that 16 and put it into S. So S of L of 12, where I put in L of 12, well, we got out 16. I'm now going to put that into my S function. And the square root of 16 then is 4. I'm going to check to see if this function really is this S of L of X. Does this do the work of both of those functions? Well, the way I can test it is I can just take that 12 and put it in this new function, 12 plus 4, and I get out, well, the square root of 16 is 4. Sure enough, I have 4 here and 4 there. So if I put it into both machines, I get out the 4. Or I can just put it in the one machine that does the work of both of them. And that, too, gives us that same answer. So, what do you think? Your first 5 on your homework, by the way, look like this. Where you're going to do some graphing. You're going to create your function. And you're going to graph that new composite function. So just like you did with your transformations, use your transformations to help you with that graphing. Then on 6 through 10 tonight, you're just going to be creating some composite functions. You're just going to find the composite functions. So let me show you. And September, what a composite function is it just takes 2 functions and it makes them so that they're one, it does the work, it creates one function that does the work of both of them. It's one function that does the work of both of them. All right, let's try another one. So you only need to graph on those first 5. You're going to get to practice using your transformations again. So if the first time you did your transformations homework, you didn't show me the parents, and I left notes on your homework saying things like, hey, show me your work, be sure and show me that parent, either the table or draw the parent on there, something to let me know that you're doing it by transformation. Don't just plug in numbers and come out with other numbers. I want you to use the transformations to graph those. Okay, so here we've got a quadratic function, and I've got another linear function. And the first thing we're going to do is we're going to create a machine, a function that does the work of both of those. So we're going to find f of g of x. By the way, I can write it in this notation. We read this as f of g of x. Or another notation you might see if you're looking online is f of g of x. Or another notation you might see is just f of g. That means f of g of x. So this, and this are the same exact thing. All of those are, we're just creating that composite function, that one function that does the work of sending it through this machine, actually sending it through this machine, and then taking that output and sending it through this machine. Okay, so we're going to create a machine that does that, does the work of both of those. I always like to rewrite it first. Instead of writing inside here g of x, I'm going to write down what g of x is. So I'm going to write down that 5x minus 1. Then we're just back to that function notation lecture that we did, where I'm just going to take this and replace the x's in there with that 5x minus 1. Like this. So I'm going to write that down without the x. Then I'm just going to fill in. This is not what we did for the early bird, is it? Did I do this one already? I feel like I did. Maybe it's different. Is it the same one? Maybe not. Maybe it's similar, but not the same. All right, so now we're going to do some simplification. Remember, this squared means this times itself. So I'm just going to simplify it. By the way, if you're graphing it, on the first 5, just leave it like this. Don't try to simplify it out. On the first 5, if you're graphing it, leave it like this so you can see the transformations. Like, then you know, well, this is going to reflect it, and that's going to stretch it, and this is going to shrink it horizontally, and that's going to move it, shift it, and that's going to shift it. So if you're having to graph it, leave it like this. But from 6 on, you're going to want to simplify. The instructions are going to tell you to simplify it. Okay, so it is similar, but not the same one. All right, so now we're going to multiply this out. So negative 2 times 5x gives me negative 10x. Negative 2 times negative 1 gives me a positive 2. That still has to be multiplied times this binomial. So now I have a binomial times a binomial. You could have done this part first if you wanted to. You could do this binomial times that binomial, and then whatever that answer is, multiply it times the negative 2. Whichever way you like to do best. So now I'm going to multiply this out. So negative 10 times 5 gives me a negative 50x squared. Negative 10 times a negative 1 gives me a positive 10x. 2 times 5x gives me 10x. And 2 times the negative 1 gives me a negative 2. Why would you do that, September? Then I've got 50x squared plus 20x plus 2. we just created a machine that puts an input into G, gets that output, puts it into F, and gets that output. But instead, you just have to put it, whatever your input is here, and you're going to get that output. So we don't have to do the work of both of them. It's just right here. Now notice that that's going to be different than if I do it this way. This time I want to find g of f of x. By the way, September, look, my son wrote that just for you then. Daring to march on when all seems impossible. Nothing's more courageous. There's your haiku for the evening. I know this seems impossible right now, this whole online thing, but we're going to keep marching on. We can do it. Be courageous. You got this. You can do it. All right, so I'm going to put f of x into g this time. So again, what I like to do is just rewrite it with that f of x. I'm going to rewrite my f of x inside of here. So 2x squared, negative 2x squared plus 4. Now, I'm going to take that and put it inside this g. So wherever there's an x in g, I'm going to replace it with this. So I'm going to take my g function, which is 5, don't write down the x, minus 1. And inside of that, I'm going to put in this for the x. So the f of x, I wrote it here. The f of x, I write it in for x in my g function. All right, now I'm going to multiply. So I get negative 10x squared plus 20 minus 1. Combine my like terms. And I get negative 10x squared plus 19. Big deal that they're different. Notice that my f of g of x and my g of f of x are two different functions. They don't turn out to be the same function. So you can't just flop it around and say, well, it's the same thing. They're two different things. Hey, Cheyenne, glad you're here. Then I can test to make sure that this is right. I can test to make sure this is right by putting in some value. So, maybe we put in f of 3 so that we have g of f of 3. Well, to find g of f of 3, I'm just going to put this 3 everywhere in there. That's 9 times a negative 10. Gives me negative 90 plus 19. 80, 71. And to check to make sure that that's what we're doing, I'm just going to take this 3 and first put it in F. So I take 3 and put it in F. I'm going to check to make sure my machine is working. That's what I'm doing. I'm just making sure my machine works. So I take F and put 3 in F. So I've got negative 2 times 3 squared plus 4. Which is 9 times negative 2 plus 4, negative 18 plus 4, which is negative 14. They don't match right now, but that's because I'm going to take this now and put it into my g function. So, I have this, and I'm now going to put it into my g function. We found that f of 3 is equal to negative 14. So now I'm going to put that in my g function. 5 times negative 14 minus 1. And I get, well, that's 50 and 20 makes 70. So negative 70. Multiply that out. See if that's right. 20 carry 2, 5, 6, 7. I think so. Minus 1, which equals negative 71. Notice that our machine that we created did the work of both of them. So I can send it through individually, or I can just send it through this one machine, and either way, we get the same output. Yeah, September, that is the hard part, is knowing where to do what. So I'll try to go a little slower next time and make sure I'm explaining that. All right, let's do another one. I'm going to do a really hard one. Super challenging one. And here's what I'm going to do. I'm going to do it in different colors, September, that maybe will help. So here's my f of x. And my f of x, wait, where did I get what from? Where did I get the 3 from? I just chose 3. I picked an input. I said, hey, let's just choose 3 to put in. You can pick any number to test it with. I think on the homework, though, I ask you to give I tell you an input. Like maybe it's 2. That I say, find this. And that's all I want you to do, is I want you to take that input and put it into your machine to find your output. But you can also try it in the other one to see where you're inputting it and you're getting this output. You're taking that output and then you're making sure these guys match. I don't know if that made any sense at all. Thanks, September. It's true. I'm at least the best at The Simpsons anyway. That's it though. All right, so here we go. Here's one that looks scary. 3x plus 2 over x plus 4. Okay, then I'm going to use a different color. And this time I'm going to do x minus 4 over x plus 1. I know it looks scary. Definitely looks scary. It's going to be okay though. All right, and what we're going to do first is we're going to find f of g of x. Or maybe we say we're going to do f of g of x. So if I wrote it this way on the homework, I would then, if I were you, I would write it this way to help me know where to put what. Or if I write it this way, f of g, I would write it this way first. So this way is my preferred way in order to find the composite functions. It just really seems to help. So what we're going to do is first thing I'm going to do is, see this f? I'm going to make him red because up there I made him red. So if I write it this way, rewrite it that way. If I write it this way, rewrite it that way. Then, this is my f, that's my g of x. I'm going to replace that g of x. I'm going to take that g of x. Yes, they are rationals. That's exactly right. I'm going to take this g of x and I'm going to replace it with this crazy looking rational. I bet you can even tell me about the domain of that thing. From Tuesday, I bet you can even tell me like what would be my problem number for x. Y'all are getting so good at it. I know at least September, she got her homework done like that. Where were the rest of y'all Tuesday night? I'll be on again tonight after this, so we can get our homework done. Or I will be on tomorrow, most of the day, off and on. Oh yeah, that bottom is what we care about. We only look at the denominator for the domain, and we say, what would make this 0? That's all we care about is the denominator. So x cannot be -1. So our domain on this one is x can be anything, just not -1. Okay, again, I'm going to leave my f red so we can see it. Okay, now what I'm going to do is I'm going to look at my f function, and everywhere I see an x there, I'm going to leave a blank. Everywhere I see an x, I'm going to leave it blank. Then I'm going to fill into that blank with this g of x function. With that function is going to get filled in. So I'm going to take what's in here and just rewrite it in there. And this time I had to write it twice because there were 2 x's. I haven't had to do that before. But I had to do that here because there were 2 different x values. So I filled in 2 different places in there. Okay, now I'm going to simplify this thing. Oof, that looks kind of crazy. But we can do it. We can do it. Oh, September, you homewrecker. Don't be a homewrecker. Don't do it. Look, see the +2? This complicated thing is married to this +2. And this complicated thing is married to that. If they didn't have an addition sign there, then we could. But because it's a plus sign, we can't. Anytime they have on that wedding ring, you have to look for the wedding ring, September. Don't do it. Well, it doesn't really have an equal sign. Think about what's on the other side of that equal sign. It's this crazy thing. This is just saying I'm finding this function. So, this is going to be some y value, but we don't know what y value it is. I haven't given it to the y value. Yeah. They do. I agree. Don't get married. Well, just stay out of relationships altogether. All right, so now what we're going to do is we're going to simplify this thing. And the first thing I'm going to do is multiply. And we know when we multiply with fractions, this is just 3/1. So I'm just simplifying here. I can't do that either, Cheyenne, because we don't know what this y value is. This is like saying a big fancy y. This is a y value to this new function I'm creating. But I don't know what that y value is. So I can't divide both sides by 3 here. And even if I did, I'd be dividing by 3 and it would still be super complicated. So instead, we're not trying to solve. I'm not trying to solve for anything. I'm just going to simplify it. And the way I'm going to do that is I'm going to multiply out first. So 3 times x gives me 3x. 3 times -4 gives me a -12. There's a 1 on bottom, so it stays x plus 1 here. Then this is just that complicated. We leave him alone for right now. So all I did in that step was I just multiplied. I just distributed. Now we're going to add up here on top. But in order to add with fractions, what do I have to have in order to add with fractions? Man, that's some craziness. If I'm going to add with fractions, what am I going to do? How do I add fractions? Do you remember? What is it that I have to have? Oh yeah, I have to have a common denominator. So ignore this bottom part for a minute. Let's just look at the denominator, and we're going to have to find a common denominator. Well, this one's denominator is x plus 1. That one's just over 1. So my common denominator is going to be x plus 1. Yay! Y'all got this. So I'm going to make a common denominator up on top there of x plus 1. Well, he already has it, so this part gets to stay the same. 3x minus 12. But on this one, I'm going to make a common denominator of x plus 1. If I do it to the bottom, I have to also do it up on top. So in other words, that also has to be x plus 1. I'm going to assume that that's a song, but I'm not really into music, so I don't know. Is a common denominator a song? I have to listen to it later now. Somebody has to teach me about pop culture, because well, I got, cool. I'm really cool. I got marker boards in my living room and such, but I don't know anything about music. So, darn it. Okay, now, leave that alone. Oh, you're close, Cheyenne, but look, it's going to be 2x. This 2 also is going to have to be multiplied by that 1. So you're really close, but I'm going to have to distribute that 2. On bottom, I'm going to do the same thing. I'm going to find a common denominator. Well, this one already has the denominator of x plus 1. So I'm going to make my common denominator x plus 1 on bottom too. And if I multiply the bottom by that, I have to multiply the top by that. It doesn't have a plus sign in between. Man, that's complicated. You can see how everything we've done this semester kind of builds up. We earlier in the semester adding those rationals together, being able to fill in with this function notation, adding fractions, multiplying, distributing, all those things just kind of build on one another. So now I'm going to distribute this. So I have 3x minus 12 over x plus 1 plus 2x plus 2 all over x plus 1. Good. That's exactly right. I'm just going to add my numerators straight across. So once I get this distributed, I can really just put it over x plus 1, right? Because I'm just adding my numerators. So here, 3x plus 2x gives me 5x. Negative 12 plus 2 gives me a negative 10. On bottom here, I have x plus 4x gives me 5x. And negative 4 plus 4 is 0. Man, that's still complicated. But remember, this is just this divided by that. We're just taking this top fraction and dividing by the bottom fraction. So how do we divide with fractions? What do we do when we're dividing fractions? We have 5x minus 10, x plus 1 divided by this 5x over x plus 1. Yes, that's exactly right. Keep the first one. Change that sign from division to multiplication and flip it. There's probably another song in there too. I feel like there is. At least there's one that's like reversed it. I don't know. Okay, so notice this x plus 1 and that x plus 1 become 1. And it leaves me with 5x minus 10 over 5x. Now, September, can I do this? Shh. Can I do that right there? Can I just make those 5x's go away? Can we do that? No! This has a minus sign there, so you can't just cancel those 5x's out. Don't do it, you homewreckers. I know y'all, you're going to try to. They're married, that's right. Don't do it, don't do it. No! They do. He does have a wife. Don't get involved, it's too complicated. Too much. Definitely taken. But maybe I can factor this 5 out. Let's separate them first a little bit. So let's factor out this 5. You know, they ended up having a kid. There's their kid. Notice this is multiplication. So this guy's single. This 5 and that 5 now can become 1. So I'm left with x minus 2 over x. Man, that was complicated. But after all that complication, when I take these two functions, I take this g of x and put it into the f of x, instead of having two different machines, I now have one machine that does the work of both of those machines. That was kind of complicated. We're going to take this same one now, and we're just going to reverse it. We're going to make it g of f of x. So it sounds really complicated there too. Let's see if we can do it though. If we can do this one, we can do any of the ones tonight. This is the most complicated you're going to get. So in this case, I'm going to do g of f of x. Some people get lazy and just call it goff. Or the other way they might call it fog. So if you ever hear a mathematician talking about fog or goff, they might be talking about a composite function. So g of f of x, for me, the way I always do it is I rewrite it in that other notation. In other words, I'm going to write it like this first. Then I'm going to rewrite it again. I'm going to take this f of x and replace it. So you know this was the f of x. I'll write it in red since it was red here. F of x. So this right here with the f here, I rewrite it like this to help me see. Then I'm going to rewrite it again, but instead of writing f of x, I'm going to write this thing. And I'm going to create this new function that does the work of, if I put this into that one, now I'm going to put my f into my g. And I'm going to make a machine that does both of those things. I'm going to make a functioning machine that does the work of both of them. Okay, so I'm going to take this, and everywhere I see an x up there, I'm going to put this in there. So I'm going to rewrite that without the x's. Oops, I wrote the x. Without the x's. Here, I'll make this one red again so we see it. Here's the red one. So see how this is f of x, f of x, f of x? I'm going to take that f of x and I'm going to put it inside my g of x. I'm going to put it inside that function. So this 3x plus 2 over x plus 4 is going to go inside my g of x function. 3x plus 2 over x plus 4. So instead of writing the x's, I wrote this craziness. Now I'm going to simplify it. First thing I have to do is find a common denominator. Notice this time my denominator is going to be x plus 4. So I'm going to have, but that one already has it, so it's 3x plus 2 over x plus 4. Here I'm doing a minus of a 4, x plus 4 on bottom, x plus 4 on top. If I do it on bottom, I have to do it on top too. So there's just the top of this. We found a common denominator. Now let's look at the bottom. Again, my common denominator is going to be that x plus 4. So I've got x plus 4, and this is 3x plus 2. This one needs that same common denominator, so x plus 4 over x plus 4. Lots of work, man. All right. So I'm going to distribute here. So on top I'm going to have 3x plus 2 minus 4x minus 16. Notice that negative gets distributed to both of them. So minus 4x minus 16. All over that denominator of x plus 4. Then on bottom, I've got 3x plus 2 plus 1x plus 4 all over the denominator of x plus 4. Simplify, so you got negative x minus 14 all over x plus 4. And here I have 4x plus 6 all over x plus 4. Keep the top, change the sign, flipping. X plus 4, change that to multiplication, flip that. 4x plus 6. Y'all are still with me, right? I didn't lose you? We doing okay on this one? I'm going a lot faster, but we've done it once, so I feel like we're okay. Are we though? I can't see your eyes to know if you're here with me or not. Then this x plus 4 and that x plus 4 becomes 1. Fabulous. And it leaves me with negative x minus 14 over 4x plus 6. Maybe. Y'all got this. What did we just find? Well, we found this new function, g of f of x. This is a new function. You could call this y. You could call him like tree function. But what this new function does is he does the work of both of these. He does the work of putting it in here and then putting it in there and putting it out. Instead, this one function does the work of both of them. So we created a whole new function. We start off with two rational functions and we put them together to make one machine that does the work of both of them. All right, that's about as hard as you're going to get tonight. I mean, that's the most complicated thing you're going to have to deal with tonight. And mainly just because it's fractions. I'm going to do one more thing with these composite functions. And then I'll go back and look at those domain problems, 31 through 34, like Robin asked about, that I didn't show you last time. I'll show you some examples of, okay? So, one last thing, though, that you're going to see on the homework tonight, I'll give you some functions like this. Let me give you first like a quadratic function, like x squared plus x plus 4. And then maybe I'll give you a linear function, like x minus 1. And then I'll give you another function like, how about another linear function like x plus 12. And what I'm going to do is set up an equation. Okay? I'm going to, oh, Justin Bieber went live. What? Who cares about Justin Bieber? I'm cooler than that. You know what? You want to watch me, not him. Is there some song about reverse it and flip it? Is there something like that? I swear there is. I'm hearing one in my head, but I don't know. Maybe I'm wrong. So, okay, so here's what I'm going to do. I'm going to give you an equation where we have to fill in. No, don't leave us. Don't leave us. Okay, so first thing I'm going to do on this side is that composite function, f of g of x. That's what this is. I'm going to rewrite it. F of g of x. And what is this f of g of x? It's equal to this h of x. So I'm going to rewrite this h of x here. I'm just going to put that there. I'm going to replace that h with that h. Oh, good, Amanda. I need to hear it. Some slight part of it's in my head. Okay, now, inside of here, what am I going to put inside of there? What is it that I'm going to write in there? I'm replacing this g of x. What am I going to replace that g of x with? See if you can do it. Well, let's look and see what is g of x. It's x minus 1. Now, I'm putting this at x minus 1 in everywhere I see an x up here. So everywhere I see an x right there, I'm going to replace it with this. This h is just staying right there. But everywhere I see this x minus 1, I'm going to put it in here. So, you know, x squared plus x plus 4. And I'm just going to take this x minus 1 and put it there, and this x minus 1 and put it there. So see how this function is equal to that function? That's what this is. This new function we're going to create that does the work of both of those is equal to this linear function. And then we're going to solve for x. So on this one, because we have these multiple equations there, it's going to actually, the last 5 of your homework, tell you to solve for x. Now we're just solving. Once we get it set up, now we know how to do that. We know how to solve. It's this setting up part that's the hard part. But now we have it set up, we can solve it. So let me write it down and solve it over here. So here's that composite function, x minus 1 squared plus x minus 1 plus 4 equals x plus 12. All I did was rewrite it over here. Now this has to be, now I'm just solving for x. So x minus 1 times x minus 1 plus, well, negative 1 plus 4 is 3. Multiply out, you got x squared minus x minus x plus 1. Combine your like terms. X squared minus 2x plus 4. Now what? Do you remember how to solve that? I'm missing x. X. Oh, I sure did. Look at this x right here. Where were y'all? I was just checking to make sure y'all were with me. Plus x plus 3. Oh, how bad. Awful, awful. I like it. Okay, so we're going to do that. Let me get back to where we were. I forgot an x. So minus x plus 1, but this plus x plus 3 equals x plus 12. I agree with you. Now combine some like terms. So that's negative 2 plus 1 makes a negative 1. Now do y'all have the same thing I do? Yay! Yes, we're going to set it equal to 0. Y'all got it. So subtract the 12 from both sides. Miss Simpson, aren't you impressed? They know what to do. They got this. X squared minus x minus 8 equals x. But you're right, I want to set it equal to 0. So now I'm going to subtract x from both sides. X squared minus 2x minus 8 equals 0. Now what? Now how do I solve it? Still don't have x by himself, and I'm trying to get x by himself on this one. What to do, what to do? Should I add the 8 to both sides? What am I going to do? You know what to do. We're going to F this thing. F it. So we're going to factor him. Once we get it set equal to 0, we just factor it. So my A is 1. My C is negative 8. So my AC is negative 8. I need factors of negative 8 that add up to be negative 2. Let's see. 1 and 8. 1 and 8. That's not it. 2 and 4. 2 and 4. Oh, I see it. And you're right, my A is 1, so I can shortcut right there. X plus 2 and x minus 4. Yay! Either this guy is equal to 0, or that guy is equal to 0. So either x is negative 2 or x is 4. So we used our composite function that time to be able to solve for our x. On your last 5, you're going to have to do that. So here's what you're going to do. First 5 of your homework, you're finding the composite function. You're going to graph those. It's going to give you a chance to practice your transformations. Be sure to show me your parent functions on those when you're transforming them, when you're moving them around. Then on the next 5, you're just finding the composite functions for me. You're just finding those composite functions. And on the last 5, you're going to use things like this where you're solving it. You're going to solve it. Okay, now I'm going to back up to that domain homework and show you the last few in there that are a little bit challenging. So let me do that. Let's back up to that domain. And in that domain homework, the last few, I just randomly give you some figures, or some domain and range values. like, I don't know, -3, 6 for the domain, and the range is like -4, 2. So what I want is for you to graph me a function that has a domain that goes from -3 to 6 and has a range that goes from -4 to 2. So think about that on my axis, what that's going to look like. It's got to start at -3 on this x-axis, somewhere, 1, 2, 3. Somewhere on the graph, it's got to start somewhere here. And it's going to go to 6. 1, 2, 3, 4, 5, 6. So my graph is going to go from -3 to 6. So starts here, goes to there. Then my graph has got to start at -4. 1, 2, 3, 4. And go to 2. 1, 2. So the range is going to start here and go there. So domain's going to go this way, range is that way. And I need just one picture, one graph that does that. That goes from here to there, but also goes from there to there. So what I like to do is, if I can, it doesn't always work out, but if I can, I'm going to look at the ones that are included. Because remember that this included means it's going to be a solid dot. And remember that these are x values and these are y values. So I can take and put a point at -3, which is an x value, and 2, which is a y value. I can put a point there. -3, 2. Then, this is an x value, and that's a y value. I can take and put a point, by the way, these are not included. So that means you're thinking an open circle at this point. And because they both are open circles, I can put a spot there. So from 6 to -4, so I'm going to make a point out of that. An x value and a y value, I'm going to make that a point. So it's 6, 1, 2, 3, 4, 5, 6, -4. Now it's everything in between there, so I'm just going to connect them. You know, you can connect it however you want. You can make it kind of dance around. Just be careful, though, that it's still a function. You know, you don't want to do this, because that's not a function anymore. If I draw a vertical line, I'm going to hit it twice. That's not a function. But you can make it dance around if you want to. You can go do-do-do-do-do, do-do-do-do-do. That's a function. Or you could have just drawn a straight line. That too is a function. Now let's check our domain. Does it go from -3 to 6? Yes. Does it go from -4 to 2? Yes. So that's all I'm asking you to do, is to draw me a function that goes from, you know, -3 to 6, from -4 to 2. Some of them are a little more complicated. Let me give you another example. This is really putting that understanding of domain and range together, and knowing that your domains are your x's and your ranges are your y's, then you can start to make points on your graph based on that. So here's another example of it, just randomly making stuff up. How about like -4 to 2 union with 1 to 3. That doesn't make sense. Union with 3 to 5. That's better sense. There's my domain, and here's my range. Let's make our range from our range can be from -6 to 8. This one might be hard. I'm just making it up on the fly. Let's see if we can do it. So we're going to have a graph that goes from -4 to 2. 1, 2, 3, 4. So -4 to 2. 1, 2. It's got to fill up this whole space. Then it's going to skip over, and it's not going to have anything from 2 to 3. Notice between 2 and 3, there's nothing on the graph. So when I get ready to do this, there's not going to be any graph. That's a good idea. Next time I will. I'm not going to put anything on the graph here. And then I'm going to go to 5. So 3 to 5. 3, 4, 5. But nothing is going to be on my graph here because it skips over that. So anything in here, I'm going to be, there's nothing in here. There shouldn't be anything in there. I'm going to have a picture that goes from here to here, skips, and goes from there to there. This same picture has to go from -6 to 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So, notice here at -4, -6, it's not included. So I can go ahead and put a point at -4, -6 that's an open circle. Then I can dance it over here however I want to. Maybe I want to make a closed circle here at -2, 1. Or maybe I want to make it go all the way up to 8. Whatever. And then just connect that. Then it doesn't really matter what the range is over here as long as it's not any bigger than that. As long as my range stays within that. So, here at 3, I can pick any of these values I want to. So your graph may look different than mine. You may have danced it around, but I'll just pick some random spot to put it. And then here at 5, I'm going to put another one, and it just has to be an open circle there. Now I'm going to check to make sure, is my domain really what my domain says it is? So let's just test it and see. Well, this picture goes from -4, goes across, see there's outputs, all the way to 2, and it stops. Here it is included, and there it is not. So from -4 to 2, that's what it's supposed to be. And then it goes from 3 to 5. Sure enough, it does. Here from -6 up to 8. Sure enough, that's what it does. So it takes some playing around with to figure it out. It's not super, I know, I always make it look easy. Hit it right down the fairway, there's no sand traps, no trees, no barbed wire fences. So great. But it does take some playing around with. I've had some practice at it. Let me do one with the infinity. So, I don't know, how about something like our domain is -4 to infinity. Or let me make that, let's make it like 1 to infinity. And then our range maybe is from -infinity to -3. All right, so think about on your x values, I'm starting at 1 and I'm going to go to infinity. So, you know, when I draw it on here, I'm just thinking to myself, I'm starting here at 1, somewhere on 1, and my graph has got to keep going forever and ever that direction. But my graph has to be at -3, 1, 2, 3. Start here, somewhere along here, and go that direction. Go to negative infinity. You know, that's what this says. From negative infinity up to 3. Well, it seems logical then that I need to put a point here at this x value and that y value. So at 1, -3, I'm putting a point. And then it's got to go to infinity and yet down to negative infinity. So, you know, towards infinity and yet also towards negative infinity. Now let's just check it and see. Did I start at 1 and go to infinity? Well, here it starts at 1. It's not included. And it goes to infinity. Sure enough, that arrow tells me it does. And then this one starts here at -3. Or actually, it starts down here at negative infinity and comes up to -3. Forever and ever that direction. So, a couple of clues. Look for when it has a parentheses, match those guys. You have an open circle. When it has a closed brackets, match those guys and you'll have a closed circle. And then you just kind of have to play with it. After you're done, check yourself to make sure that it really does match that domain. And we may all end up with different pictures because, you know, I just picked points here. I could have done this different ways. I wouldn't have had to do it that way. I might could have done it where maybe on this one I start at -4, but maybe this -6 I put at 5. You know, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. I might could have put that there. And then I could have done this 8 and this 3. 3. 1, 2, 3, 4, 5, 6, 7, 8. So, you know, maybe I did it like this instead. And then from -4 to 2, maybe I did some 1, 2, 3, 4 to 2. Maybe this was an open circle and this is a closed circle. Maybe I do some dancing around like this. Let's just check it to make sure. My domain goes from -4 to 2, skip from 3 to 5. My range goes from -6 all the way up to 8. I have an output for every one of those. So you can see how our graphs may look different and yet they both have the same domain and range. So on that one, I don't even give you answers because of that. On those last 4s, there's an infinite number of solutions to it, how your picture might look. So it does take some critical thinking. It does take you to make you really stop and think about it. Just remember the brackets mean closed in circle, and the parentheses mean an open circle. And then after you're done, check yourself. And then don't make it, I say do a function. So if at any spot you can draw a vertical line and hit it twice, it's not a function. So make sure that you've got a function. You know, this is not a function. This is not a function. I'm going to hit it over and over again. So just make sure that you are drawing a function too. That's the other thing on that. All right, my plan is to get on Discord. And I'll be on there tonight to help you if you're wanting my help on it. And then I'll be on tomorrow, off and on throughout the day tomorrow. And Then Saturday, maybe a little bit, but I'll be making a lot of videos on Saturday. But I will be around on Saturday, off and on. Get it done by Saturday. Get it into the Dropbox. Y'all get it done. Come on, guys. Come on, come on, come on, come on, come on, come on. And then I'll see y'all on Tuesday. You got this. You can do it. All right, see y'all Tuesday. By the way, Math Made Simple at Simpson Math. Thanks for watching.